I was talking to one of the colleagues, the participants, and that there are so many equations. So I was going to actually test you a little bit. Do you remember all the equations? But any questions? Any things you would like to say about all the things we did yesterday and the day before?
I must say I was very happy to see how you used the entropy balance to gain information. Do you know any other situation where that is used so actively?
Yes, there is a huge literature in what they call rational thermodynamics. And then they looked at the most complex materials, materials with microelasticity and with, there are some names for them, even non-local materials. And non-local material is when the mass balance doesn't hold at a point, because a point can break into 2 points. For example, when fracturing occurs or tearing occurs. So if a cloth, you tear it, a point becomes 2 points. And for those materials, is the integral of the total mass that's constant. Not locally at any given point mass being constant. So the mass balance equation holds only in an integral form. So they apply to that, they are really, yeah, it's over, and these are even things that I know are from 35 years ago when I was learning these and I saw who is doing what. And after that I was more involved, okay, applying to the porous medium, two-phase flow, and once I got the equation, then I have been really busy with the, okay, what do these equations mean? In terms of, yeah, parameters, can you measure them, how much they are, and also in terms of solution, how does the solution now behave? I give some examples the day before yesterday that if you add that dynamic term, tau dsdt, you get monotonic. And now there is already a big literature on that order. So yeah, it's been applied to many other.
Yeah.
The ingredients you need is the balance laws. So if you have some sort of process that you have your own balance laws for it, okay. As part of the balance law is, okay, what is the balance of entropy? Although the form is, now, the time rate of change of internal entropy density function, the flux of entropy, supply of entropy, and the exchange of entropy with the neighboring continua. And this must be non-zero. And what are those terms? Those are, then becomes what the art that you, art of that particular area. I hope that answers your question. Any other questions? All right. So, another thing I hope you got is that I have tried to avoid throwing in terms. If anything, I remove terms. And if you notice, when we start with the, we'll have more of that day, axiom of causality and determinism. We say, okay, all the effects, all the fluxes and the density functions are functionals of motion of all times and all points. Now, I think that's the most general you can say, and yeah, do you need to prove that? I don't know. I take it as the starting point. And then after that, we throw away terms because we say, okay, yeah, not all points of the space, only the neighboring points. So the gradients we take, not the second gradient. Not all past times, only the first time derivative. Velocity is the derivative of motion. So the last 2 times, recent times. The rest we throw away. And then when we go through the like things like here, we say this tau is a function of VFS, the velocity difference between fluid and solid, is a function of temperature gradient, is a function of temperature, is a function of density. Now, so it's a function of those, and we simplify. Say we make it linear. And this is opposite to say, oh, I have this equation and I need dependence on temperature gradient, so I throw in a temperature gradient. That's the, too often has been the empirical approach, the way the equations have been developed. And then we get momentum equations, okay, we neglect the inertial term, and if you neglect the temperature gradient, now then you get the Darcys law, and so forth and so forth. Okay.
And this is only for one fluid, right?
That was only for one fluid.
Yes.
And a single component fluid.
Yeah.
So I thought, actually, I didn't have that planned originally, but there were questions about how about if there's chemical potential, where does chemical potential come in? And I thought, okay, so I look at a 2-component fluid, a 2-component liquid, in a porous medium.
Okay.
So that means, say, water and salt. Now, I must say, if that component is present, the second component is present in tiny amounts, the trace amounts, you will not expect that it will affect the motion of the fluid, the motion of water, because the number of molecules are so small, it doesn't affect the molecular movement of the water. But so at the start, we assume that we have water and another solute, say salt, that they are both present in, say, comparable amount. As you know, salt you can dissolve up to 311 grams per liter under normal conditions. So that is, on mass basis, 26% of brine. So let's say if you have a lot of salt, would that have an effect on Darcys law, for example? So we start with balance laws. I'm not going to go through the, I'm going to give you starting at the molecular motion, because it's a simple system, and then for 2-phase flow it's good to have had this, and then it's hopefully helps with the 2-phase flow. Okay. I think it's this one. Yes. So now we consider that we have 2 types of molecules. You can actually say more types of molecules, but let's just say 2 types of molecules. So they are, we used to say when it was a single component, a particle was denoted by particle I. And then I is just ordinal number. You have a zillion particles, 1, 2, 3, 4, up so. Now we say, okay, we have particle 1 of type alpha and particle 1 of type beta. So there are 2 types of particles. And so the I is the ordinal number, just counting the particles, and alpha and beta are types. You can see the color of it. And they, each of them have their own mass and their own position vector. And then we had this, that we say the velocity vector is the time derivative of the position vector for each particle separately. Oh. Okay. Good. And then there are intermolecular forces. Now, there are intermolecular forces between particles of the same type as well as particles of alpha and beta. They exert force on each other. It's not okay, because they are miscible, mixed, they see each other all the time. But so I don't put any alpha or beta here. Any particle I of any type exerts a force on particle J of any other type, and you still have this relationship. And then there are long-range forces that apply forces on these particles, and these two forces are not necessarily the same. Although if you think of gravity, no, they would be, of course, the same acceleration too. Yeah, I must say the way I think this was introduced, there is m in here, so then it is different. Then we write the conservation of mass, and we say the individual particle of a mass, individual particle of type alpha has a constant mass, and the total number of alpha molecules are constant. So this is a non-reacting mixture. Salt and water do not react. And the same holds for beta particles. And then we say the second law of Newton for particle Pi of type alpha is that the momentum of that particle is effectuated by the forces acting on that particle by particles of alpha type and by particles of beta type. And these are the numbers of each, plus the external forces. So now we have this extra force compared to when it was single component. Okay? And then we define an Rev, or we define this psi function. I didn't do that. You could also assign different psi functions to the different type. This is all possible. And then, therefore, the mass density of alpha component will be the sum of all mass of all particles of alpha over the whole space, but then weighted by psi. And the momentum is defined as the sum of all the momenta. Okay? And we have exactly the same for beta particles. And if you now add them up, yeah, actually this must be 0 because they are not exchanging mass. So this is not correct. Sorry about that. This is simply 0. Okay. And then we do the averaging, and by averaging, the way we do is that I didn't, by the way, go through the derivation of mass balance. We did it 2 days ago, and it's exactly the same. You take the derivative of this, and then by virtue of the chain rule of differentiation, you can see that here you get d psi dt and then dx dt, and that is velocity, and then you get divergence psi. Okay? So I didn't do that. For the momentum, we take the momentum balance for an individual particle multiplied by the distribution function and sum over all particles of alpha. Now, this way, again, we have the same issues we had earlier. We move this ddt, we put psi inside the ddt, and then we can get an extra term because you have to have product rule minus d psi dt should be subtracted, and this part gives you the time derivative of momentum, and that second part gives you 2 terms I'll show in a minute. And then for the forces, again, you have 2 different forces. You sum for all the alpha particles of those forces. This is also over alpha particles. So we have now 2 types of forces. component forces, intra-component forces. So you can say this is a sort of stress tensor within that component, or stresses within the component, and inter-particle forces, and this is a sort of body force that is acting upon it. The difference between these two, I make a distinction, is that this one, because Fij alpha and Fi of two particles on each other are 0, and you average over particles of all particles of alpha, inside a body is always 0, that sum. Because this particle exert the force, I sum over both of them, gives you 0. Only at the boundary, or if you put a surface and you average over on one side, then you have force, exchange of force on the other side. This one is everywhere. And if you sum it inside, it doesn't go 0, because we don't sum over all particles. We don't sum over beta particles. We sum over only alpha particles. So this is a kind of distributed body force, similar to this, but this is coming from outside wall, this is inside. And these are two different force types. So we put everything together, we get this equation we had for single component yesterday. There is this, which is the average of deviatory. So this D, if you recall, is the sum of M of alpha Vi hat alpha Vi hat alpha, then times psi function. Okay, and we say that this is a tensor that accounts, and notice that there is a minus sign missing. I do this all the time intentionally. I did that. I say, oh, there's a minus sign, you forgot. But yeah, okay. So there is this term in here, and that is the term, as I said, is a surface force, and you can show that that term can be written as the divergence of a tensor. This is a vector and can be written as the divergence of a tensor. Okay, and if we put these two, and this is, let's say, T prime, make a distinction here, and then total stress tensor is the sum of these two. So this T is really T prime alpha is a tensor minus D alpha. Okay, and that gives you the momentum balance equation with one extra term. This is a body force within the whole. Exchange of forces between the two components. Okay. All right. Now we can then do the same for the energy. We can get energy balance. I didn't think it was necessary to go through this, and we should be here. Yes. So we can get the energy balance. Didn't go. Ah, okay. Yes. We can momentum balance and entropy inequality. All the equations I showed you, I just wanted to show that for these two component system, you get these extra internal interactions that's everywhere between the particles. So now let's look at the balance laws. We have this balance of mass for the water component, for the solute component, or salt. I just put solute to make it general. What I also didn't have in the short derivation I just gave you, I didn't do it for porous medium. That was just a single liquid. But if you go porous medium, we did that yesterday, you also get the volume fraction or the porosity in here. So compared to what I just showed you, we have this porosity. Okay, now this is the pure water component. This is the H2O. This is the salt. We can put these together and define the fluid, the liquid as a whole, the brine. And for that, we can say that the mass density of the fluid is equal to rho of mass density of water plus mass density of salt. I don't know why it doesn't like it. Because this is mass per volume of pores of water, mass per volume of pores of the salt component. Water and salt are filling pores simultaneously. They are everywhere inside the pore. It's different from saturation, that when you have two immiscible liquids, they are not filling the whole pore them simultaneously. They are separately filling parts of pores. But they are filling all pores separately. So that's why it's mass per volume of pore, mass per volume of pore, and therefore this is the mass per volume of pore, and which means mass density of brine. So if we put these two together, then we get the mass balance for the brine, for the whole liquid, the single phase. Okay? Then what we do is we say we can also write the equation for solute in terms of mass fraction. So we define the mass fraction of solute as the density of the solute divided by density of the whole liquid or the whole fluid. And if you do that, the mass balance for the solute becomes this. Because if you talk about solute transport, you are used to see a diffusion equation, right, for solute transport. So what is the diffusion equation here? It's just a time derivative and a divergence. The diffusion is in the fact that the velocity of the solute is different from the velocity of water component, and for that matter, it's different from the velocity of the fluid as a whole. That's diffusion. So that's why we define a diffusion velocity, which would be, I show that with ui, and this ui is the difference in the velocity of the solute and the fluid. No, okay. So these are vectors. There's a vector sign. Okay? And this is the diffusion velocity. So now if we use this in here, we get and subtract the multiply by the fluid mass balance by omega, and subtract from this, what we get is the omega dt. Then we have, this is the divergence, so it should be a comma here. Let me put that in here. Otherwise, I added this last night, and I think I was too tired. So there's a comma here. Comma indicating the derivative. Do you are you familiar with that notation? So the subscript comma k means the derivative, the divergence of omega. So here you have the advective term, here you have the time derivative, and this is the diffusive term. So this is diffusive mass flux of solute. You can show this with J if you want. There are and then I need 10. So this whole thing, you can also write it as J, K, K. So that is your diffusive term, actually. And we are used to say, okay, JKK from Ficks law is minus diffusion coefficient times the gradient of mass fraction. If you put that here, you get the diffusion term. That goes to the other side. Is that, can you agree to that? Okay. All right. So this is my mass balance equation. I also have momentum balance laws for the whole fluid and for the solute component. The whole fluid has exactly the same form as I presented yesterday for single phase flow in a porous medium. The fluid as a whole has a stress tensor, has an exchange of force with the solid. And this is, once again, Reve scale, so appears here as a body force. It's not at the boundary of pores, because at this scale, boundary of pores don't exist anymore. You just have smeared out two phases. And then for the solute, we have similar construction, but now the solute has this body force receiving from the water component, and it is also interacting with the walls of the pores with the solid, so it is a force coming from the exchange with the solid phase. And there is an energy balance. It's a reduced form. I give the energy balance here only for the fluid and not for components and water and solute. The reason is I am going to assume, or I already actually assume here, that water component and salt component have the same temperature. I think this is reasonable. The molecules are so intermixed, you could not possibly imagine that the salt component has a different temperature than the water component. So I assume them to be the same, and because of that, I don't need to have separate energy equations for salt and for water, and I just give it for water, for the fluid. And then I have an energy balance for the solid. So you see that there is an exchange of energy between fluid and solid. And the sum of these are not zero, because we also have exchange of energy through these forces. So there is a different restriction on that. Any questions so far? Okay?
Yeah. Why isn't there symmetry in equation 46 and 47? Solute has two of these big T's, but water doesn't.
Yeah, so this is not water, this is solute and water together.
Okay. Yeah.
So this is the brine, let's say.
So this is brine.
I use W for the water component, I for the solid component, and then F for the company.
Now I see.
So it was, there is another equation here for the water component, and then those two terms cancel each other when you add them up. And the sum of interaction between solute and solid and water component and solid gives you the total interaction. Yeah. Okay, so now then we say we want to propose a constitutive theory. We identify constitutive variables, and here I have chosen density of the fluid. I must say I didn't go through the whole starting with dependence on all past times and all points of the space, and then axiom of a smooth neighborhood and short memory. I didn't do that, so I have already chosen what I think are the most relevant independent variables. I have also said it is rigid solid, therefore I didn't include porosity. That can be done. That was not major issue. So mass density of the fluid, the brine, the mass fraction of the solute, the gradient of mass fraction, because we know from experience that the gradient of mass fraction will make things happen in the medium. And the diffusion is that. So we must have a dependence on that. Temperature, I didn't include temperature gradient. The velocity of solute and the velocity of the fluid. And then because of objectivity principle, I cannot have absolute velocities. I must have relative velocities. So then I put the velocity of solid with respect to fluid. That's the diffusive velocity, and velocity of fluid with respect to the solid. Okay, so this is because of objectivity. Okay. Now, I am also not going to go through the whole derivation of exploiting entropy inequality. It's becomes too boring. We have done that yesterday, and if you do that, I get this kind of results. The free energy of the fluid is a function of density of fluid, the mole fraction, and the temperature. You know that you can class the Gibbs-Duhem equation you can derive by this. If you take the derivative of this, dAf will give you the pressure basically times d rho, and chemical potential times d omega, and entropy times d theta. It can come from this. For the solid, it was rigid, so it's just a function of temperature. For the components, I didn't go through it, we get information about, always about the relative to the water or the fluid, the information we get. So what is the difference between free energy of component and the solid component and water component? So this is a sort of relative free energy. And we can find that this is a function of mass density and omega theta, the same as that one. The sum of the entropies of internal entropies of the whole system is related to the change of temperature of the whole, rate of change of free energy of the whole system. This you can see that you can write it as minus dA total. D theta. Yeah. The total free energy with respect to
A total is AF. Or what is it?
Total is A
F plus AS.
epsilon F rho F. AF plus epsilon S rho S AS.
Yeah.
Of the solid and the fluid.
AF is equal to AI plus AW.
Weighted with the rho's. Rho FAF is equal to rho I omega I AI plus rho W omega S.
Okay, and so you do the same for the total AS.
Correct. Okay, what I get for the stress tensor in the fluid as a whole is not only a pressure term, which we usually get for the, we potentially have a contribution from this diffusion of velocities that comes out of the, so that means if you really have a way of put an instrument in the liquid and measure, that instrument measures not only the movement of say all the particles hitting it, but there is an extra momentum exchange due to this diffusion of movement of the particles. I don't know whether this has been anyone has any explanation or better insight what this means, but this came out of the entropy inequality.
I'm trying to relate it to the quantities I'm used to.
Okay.
So I wonder, if the relative chemical potential is fine, but there is another internal relation, the Gibbs-Duhem equation. Will you also get that out of your setup?
Gibbs-Duhem equation, wasn't it that DE is with the DE, right? The D of internal energy.
The chemical potential of salt is intimately linked to the chemical potential of water.
Yeah, that is here.
Maybe no, because it's a difference. In the water uses a reference, so there's one, you have only n minus one difference.
It's the relative chemical potential.
It is some ratio difference.
So the relative chemical potential of salt, so that is difference between chemical potential of salt and water, is linked to the change of free energy of the fluid with respect to mass.
That is fine.
You don't mean this one.
There is an additional internal relation.
And what is that?
That the mu of the I is times the composition is plus the same contribution from the other is 0.
Yeah.
Constant temperature and pressure.
Yeah, at constant temperature and pressure.
Maybe we should then sit together.
Otherwise, there are
I have given
additional terms.
a selection of the equations that came out of the entropy inequality.
Yeah.
And so it could be there is something there that I haven't given here because I thought these are the relevant ones. And hopefully these are all familiar to you.
This 54E, would you say that the last term will give you osmosis?
No, osmosis will come in a minute.
Okay.
These are just definitions of that there is a relationship between these thermodynamic quantities, that there is a relative chemical potential of salt. It's still a function of the same quantities as the Helmholtz free energy, density, mass fraction, and temperature, and it is related to it's equal to rate of change of free energy of the whole fluid as with the change of mass fraction.
Just one question again about 54E. I mean, yeah. So the last term in say the normal irreversible thermodynamics probably would not be there because it's quadratic in gradients, isn't it? It's the diffusion current to second order.
But this is not the diffusion term that goes.
No, but the U is
the diffusion velocity.
Is non-equilibrium term, right?
Is
non-equilibrium. It's not there if the system is completely in equilibrium.
That is correct. If you have equilibrium, it will be 0.
So it's a second order term. So it is.
Okay, that's correct. You say that if you measure pressure under equilibrium, then it will not be there. But how about if you measure pressure under non-equilibrium?
Well, then it will be there, but it will be much smaller than all the terms that are linear in the gradients.
Yeah, I understand. Yeah, unless you have a huge diffusion flux, and when you have high salt concentrations.
I'm not saying it's not there. I'm just saying it's not linear in the gradients.
That's correct. Yeah, that's correct. Yeah. Okay. So these were these thermodynamic relations. Then I also have equations which I already substituted here, saying that, you remember we had this, what is the mass balance? We had this T hat Fs, and we have this T hat IW, and T hat IS. Those I get equations for them, and when I substitute, those terms have an equilibrium part and a non-equilibrium part. The equilibrium part cancels here pressure times gradient of porosity, and only the non-equilibrium part remains. So this is you can say force. Here. Sorry. So this is a function of the velocity of fluid with respect to the solid, the function of the diffusion velocity of the salt, and it's also a function of, now all the other ones, temperature, omega, no, porosity was not included. So it's a function of these. So this is the diffusion velocity. And the same in here. This is a function of velocity of fluid with respect to solid. So all the functions we had in the list of independent variables. This is the momentum balance equation I get for the salt component. I have not thrown away, I have thrown away only inertial terms. I've thrown away inertial terms, and that's the only term that survives for the salt component. This is the momentum balance. This is momentum balance for the whole fluid. This you can recognize. It gives you Darcys law. And this actually gives you the Ficks law. And we see that in a minute. If you now assume, now this is the residual entropy inequality, that the product of this interaction force between fluid and solid, and the velocity difference between fluid solid, and the interaction force, the component I and the other component, multiplying by the difference in velocity must be non-zero, non-negative, and they will be zero at the equilibrium because these terms will be zero at equilibrium. The velocities will be zero at equilibrium. Now, if I assume a linear relationship, so I linear the friction force basically between water and solid, and I have two terms. One is the velocity of fluid with respect to the solid, and the other one is the diffusion velocity. And the same holds for the solute. Interaction force for the solute is a function of these. So if I put that in here, now you see this is a Darcys law, but then with a chemical potential effect. And for the solute, I had here the gradient of diffusion. I have here the gradient of chemical potential. This is gradient. So I expand that because chemical potential is a function of omega and rho. I expand that in this fashion. And here I get a momentum balance for the solute. If I throw away this term and this term, I get Ficks law because this is diffusion mass flux. I show that here. See, the Ficks law is concentration gradient, mass fraction gradient with some coefficient that relates to the change of chemical potential with mass fraction, and then there is a resistivity tensor that if you put it on this side, you get Ficks law. And you get Darcys law if you neglect the chemical potential part. But if they are not small, then you must include them. Okay, so this is similar to some of the Onsager relationships that you also meet. Now, one thing that I wish I had time, and maybe I do that later, that came out of this work when I did this is the following. I was working on a project related to disposal of radioactive waste in deep salt formation, salt domes. As you can imagine, the salt dome itself, it doesn't have much water, but around it there is water, and the density of water is almost saturated brine, and it comes up, and there are some places sharp gradients in density. All of a sudden the density drops from very highly brine density to sort of seawater density. And the question was, if this radionuclide waste that is put in there in the salt dome is not supposed to come out, but yeah, they will remain active for 100,000 years. So in 100,000 years, no one knows what happens. if these radioactives come out of this salt dome for any reason, now it could be that in 25,000 years from now, people will be looking for things they drill and they drill directly into the repository. Okay, now the things come up. So would the dispersion of these radionuclides in water in a brine environment, when you can have large concentration of salt and large concentration gradients, would it be different? Is it just Gibbs law of diffusion, or would there be more? So we did experiments. We did column experiments where we had fresh water, and then we brought in salt water and looked at this diffusion, or actually it was dispersion because it's porous medium. And we did that with various salt concentrations. Now, when the salt concentration was low, even up to seawater, we get the typical S-shaped breakthrough curve, which you could model with the diffusion equation. But when the salt concentration became larger, we got very funny shape. It was not S-shaped, and you could not possibly model it with the diffusion equation. So if you look in here, one of the major assumptions is that there is a linear relationship here. And we always know that, for example, Darcys law is valid if the flow velocity is not large. If the flow velocity is large, yeah, we get Forchheimer equation. That means the linear dependence of this friction force, interaction force, on the flow velocity is not valid anymore. You need to add a second order term. So when you have very large concentration differences, gradients, you will have very large diffusive mass flux or dispersive mass flux. Then the linear relationship is not valid anymore. And you have to add a second order term, or higher order. We added a second order term, and now these are all published and others also looked at. You get perfect fit of the breakthrough curves at higher concentration gradients. So I think these are the strengths of this approach, that you do observation, either yourself or I came up with these constitutive equations saying, yeah, that's how your system should behave, and you tell me, no, it doesn't. Okay, what is wrong? And then there are various candidates. We go back. Somewhere we made these assumptions. Sometimes it's because we just didn't include the right state variables. Remember, we had a set of state variables. We didn't include the second gradient of mass fraction, for example. Maybe we should have done that. And you can then include it, go through the procedure, see what is the final result. Does this help? Yes. Well, perfect. No. No. Go back again. That's the kind of iteration you should do.
You basically just assume that the R and the V's in the top equations can depend on the velocities.
That is correct. Well, you can put it that way, or the way I propose this is that, okay, this is a function of velocity and UI.
Yeah, because it is always zero for zero velocity, so it's sensible to keep the form of the equation and just take R and B dependent on these
You could do that, but the problem is that in one-dimensional, it doesn't matter. But when you go to higher dimensions, then you have this vectorial nature. Then you have, this is a tensor. How does a tensor depend on a vector? Now, you can always say it only depends on its magnitude. Okay, yeah. But how about if it is more general than that? So I would always say, do a Taylor series expansion. And if you do a Taylor series expansion, then you get a first order, you get second order. And when you do that, then sometimes you can see that actually a second order cannot survive because the tensor multiplied is a third rank tensor, and under certain symmetry condition it cannot exist. So those things can also happen.
And did you add quadratic terms both in the velocity Fs?
No, only for
in
this.
U.
Correct. Only here.
So only the relative, the diffusional velocity.
Correct.
Yeah.
Yeah. Yes.
And
Okay.
You satisfied the second law, I suppose.
Yes, yeah, oh, absolutely. Everything must satisfy. Axiom of admissibility.
Yeah.
That's the nice thing, that the axiom of admissibility from an entropy inequality gives us 5, 6, 7 equalities. And that's the beauty of it. Okay. I hope it's not too boring. I mean, this kind of equations time and again, because I have more of these. So maybe we should take a break then.
We'll be back at 10.